Alrighty, good morning, guys. Can you hear me?
Yes.
Oh, how are we doing?
I'm a little tired right now, but doing
So
all right.
we're going to finish up the material needed for next week's exams. And let me just show you. Let me just show you the schedule. So most of you have signed up, but there's still about a third of the students or so that haven't signed up yet. So if you go to Zoom, what is it called, Canvas, I put in under announcement, I updated the schedule a little bit. So you can see here under announcements, you can see all the students that have replied. So if you haven't replied, now would be a good time to do it. So I can get you in here. If I don't hear back from you at some point, I will schedule you in. The first slot is on Monday, so 5-6 days away. So here are the slots. The thing to know is that to connect to the exam Zoom, you have to go through your Zoom account. It will not work if you're used to hooking up through Canvas. This is not going to work. And this is done to authenticate. So set up a Zoom account and log through your Zoom account. It will not work if you try to go through Canvas. Okay, so the link is here to set it up if you haven't set up your Zoom account yet. It's not a big deal. Okay, so the exam is going to start. You can see the time slots here. So we'll start the exam by, I need to see your face and then your ID. You need to have some sort of preferably your Rutgers ID. If you don't have that, if you have a passport, if you have a driver's license, something that has your ID and your name on it. And then the other thing that comes is we need to decide on what kind of a media you're going to be writing on. If you want to write on a document camera, if you have a phone, or if you want to use your computer's camera to write on, you can do that. If you want to use whiteboard that's built into Zoom, you can do that. So let's try to do that just to set it up so you can see how it looks like and what kind of features there are. If you want to use that, there's a little bit of action on your end that you have to do. So let's try to see if we can get this to work. There's a button, and under that button, you have to click this annotate. Okay, so there's a view option button, and under that you have to click annotate. Okay, so I'm going to set that up now and see if we can get it to work. Okay, so I'll share the whiteboard screen. Okay, so now you should see the whiteboard screen, and you can write on it. Then there should be an option button, and try to click that, and then under that click annotate, and then see if you can write on this piece of paper again.
Professor Larson?
Yes.
So I have given my preference for the oral test, but I don't see my name in there.
Okay, can we play with this whiteboard first and see if we can all get this to work?
Sure.
So try to write something on the whiteboard, and then you'll get your name figured out somewhere. Okay, so far nobody has written on the whiteboard. Can you not find the button? There you go.
I'm using the web browser right now, so I don't think I can access the whiteboard.
Can you say that again?
Um, I'm using the web browser version of Zoom right now, so I don't think we can use the whiteboard.
You're breaking up when you speak. So
Okay, so if you can hear me, I'm just saying that I'm using the web browser version of Zoom, so I can't access the whiteboard right now.
okay. So can you only see the whiteboard, or can you not
Yeah,
access?
I can only see it.
So I can see some students are able to get this to work. So you can both write in text, and you can write with your pen. If you have a tablet, it should be possible for you just to write directly with your tablet.
Professor, can you show me once again where can I find the whiteboard?
It's right there on your screen, right? Can
Uh,
you see these scribbles that people have made?
yeah, I can see the screen, but I'm not able to do anything.
Okay, so you have to find a button.
You look at view options and then scroll to annotate.
View option. Oh, I have only two options under view: show manage participant and show chat. That's it.
And so are you using a web browser too?
Yeah, I'm using the web browser too. Okay, let me try with the app then.
All righty. Is anybody still trying to get it to work? I will say if I mean, most of you guys probably have a phone, and it's not difficult to turn your phone into a document camera, and that will allow you to write on a piece of paper and just have you can stack up books, and you can just flip your phone around so the camera points down to your paper, and you can convert your phone into a document camera, and you can write on a piece of paper, and that will allow me to see what you write in real time as well. And there are lots of YouTube videos that will show you different stands and different tricks and on how to get your phone turned into a document camera. And there are even professors at Rutgers that use their phones instead of, I have a document camera here, but you can easily well just use a phone here. This could have been your phone instead of a camera, and use that. So it's up to you what you guys want to use. Then there was a student that said that you had reached out to me for, I'm going to stop this now, so hopefully you played with it. A student that reached out and said that you were not scheduled. I probably got you into the wrong class. So can you send me either your name out here in the log, or send me an email about it, and I'll get you rescheduled. Okay, are there other questions or comments before we get started? There was a question about if we can take it at different times. So I would very much prefer that we all take it during these time slots that are up there. I have 50 students that need these oral exams taken, and it is not very easy to keep track of 50 students floating in and out between these two courses. So please try to make these time slots work. They've been posted for more than, when you've been up for what, 5-6 days at this point. Please try to make these time slots work. Are there any other questions or comments about the exam that's coming up?
We have a recap on all the stuff that we'll be learning about, that we've learned about for the exam.
Can you say that one more time?
Will we have like some kind of review or recap session for what we got to learn for the exam?
I mean, there will be office hours on Thursday, as usual. This Thursday and this Friday, there will be office hours, and
Okay.
whatever questions or comments that you have, we will try to answer them. The TA has rescheduled his office hours for Monday and Tuesday nights, and
Okay.
so we'll go through. I mean, today again, we will talk about things that we have talked about a few times, but there'll also be new material today. We got to wrap up all the loose ends, so you're prepared for all these questions.
Mm-hmm.
So there's another question. Are the exams questions exactly the same as the ones on the midterm? No, they're not. The starting point is these questions that are posted out on the on Canvas. That's the starting point, right? So depending on how it goes, you will be asked other questions, and these other questions, they may or may not be from those sheets of problems. This is not about you taking these questions, memorizing them, and copying them on a piece of paper. This is not how it's going to be. Like, you will start writing, and then I'll start asking you questions, and then we'll see how it goes. So some of you have talked to me in office hours about trying to memorize all these answers. So I do not recommend trying to memorize answers to questions. This is not going to work. You've got to try to understand it. Okay, anything else before we get started? All right, and then let's get started. We've been talking about pricing derivatives, and let me go over the general method one more time, and then we'll do an example. So we're pricing derivatives in a multi-period binomial model. And so remember the starting point. It is, we have the size, the IID coin flips. Right. So they look like a U, and you take the values U and D, probability P, and 1 minus P. This is your psi n. And then you create the stock. The stock is given by an initial value. I'm going to say it's positive. And then we define it recursively by saying that the next stock price is given as the previous one times the outcome. Are there questions again? So about, can we take the exams at different times? So please try to make these time slots work. Yeah, this is making it the same for everybody. These time slots you announced at the same time for all students. Please try to make them work. As I said, I have 50 some students that need half an hour each. It is not so easy just to squeeze somebody in there and take somebody out there. Please try to make these time slots work. If I start scheduling one student at a different time, then somebody else is going to need to be scheduled at a different time too, and so on and so forth. It's not very easy on my end to make all this stuff work. So please try to make these time slots that we have listed, we just looked at them, please try to make them work. Okay, so let's go back to starting out with a positive value for the stock, and then we recursively define the next stock price as the previous one times times the outcome of this Bernoulli, this coin flip random variable. And of course, we also have a bank. And the bank defined very similarly, we're going to start the bank out at, say, just 1. And then we're going to get the bank value by taking the previous one and then times 1 plus r. Right, so this one here, this is not random. So when we say not random, people also call that for deterministic. And this one here is random. And that's because of the science. Right, so the stock, you don't know what the stock price is in the next period because it depends upon the outcome of the coin flip. The bank, you know what the bank is at the end of the next period because the interest rate R here is a constant. Okay, so then what we're given is a derivative. So a derivative pays out Fn of Sn at time n. For a function, this is a function. So the examples are the usual ones that we've had before. Fn of x could be.
Is that a derivative payout?
Yeah. Yep. Right. A derivative pays off Fn of Sn at time n, where Fn is some function. For example, like a put. Right, so there's nothing random about Fn. This is Fn is not random. It's just a function. Right, but then you compose it with Sn and you get a random variable. So then the name of the game is you have your binomial model, which has these legs that have been moved out. So you're sitting out here time n. This is where your Fn of x is to be thought of. And then what you do is, your goal is to figure out what is the price over here at time n. And so what we're going to do is this method that we're doing is dynamical programming. So we're going to iterate from the end towards the beginning. So the first order of business is to move back one step. We move back from Fn to Fn minus 1. So this is going to be our job to create this function here. And so on. So we're going to do all these functions. We're going to end up here with f0 of x. Okay. And the way that we do it, we're going to use, this is from last time. We're going to use that x tilde n, which is defined to be xn divided by the money market account. That this is a p tilde martingale. So what that allows us to do is, so we're going to use this. So we want a wealth process. We want xn, this is our wealth. We want xn to be this Fn of Sn. This is the replicating property. So now we want to go from out here at time capital N and then move backward. And so if I want this, then this is not surprisingly, the same thing as saying that if I divide by 1 plus r, this is the same as wanting this quantity. So if that's true, then the conditional expectation, so we need the conditional expectation given fn now minus 1. This is how we move the payoffs back in time. You move it from time capital N to time capital N minus 1 by conditioning. And the reason that we can do that is because of this martingale property we're going to be using in a second. So this is the same as the conditional expectation of Sn divided by 1 plus r given fn minus 1. And so here comes when we use the martingale property, right? This here is equal to xn minus 1. But this here is the martingale property. This here is, this uses xn tilde is a martingale. And the reason, how do we go for the xn tilde being a martingale to this property? There are no tildes on the x's here. Well, the way that you do it is you say that the conditional expectation of xn plus 1 given fn with the tildes on top, this is exactly xn tilde. And now you use the definition. You use the definition that this is x divided by the bank. This here is the expectation under the tilde measure of xn plus 1 divided by 1 plus r to the n plus 1 given fn. That this is equal to xn divided by 1 plus r to the nth. And now you can see that the 1 plus r to the nth is going to cancel out the 1 plus r to the nth here. You will cancel out, and you'll be left with this property here that when I divide by 1 plus r here, I'm going to get exactly xn. Okay, so your wealth at time n minus 1 is this conditional expectation. So let's work out what this conditional expectation is. So this thing over here on the right-hand side, well, I had 1 plus r outside. And then I can plug in the definition of Sn. This is Sn minus 1 times the nth coin flip. And then I can use the independence lemma. I can use the independence lemma because here the stock price at time n minus 1 is measurable, and the nth, capital Nth coin flip is going to be independent. So I can use the independence lemma, and the independence lemma says you take out what's measurable, replace it by a dummy, and you take the average over the rest. Okay, so I freeze the thing that's measurable, and I take the average over the rest. I will get 1 over 1 plus r. I'll get p tilde. And I'll have fn here, Sn minus 1. The coin flip is going to be u with probability p tilde. So I'll put that in, 1 minus p tilde over here, fn Sn minus 1, and then a d. So my wealth at time n minus 1 is given in terms of this function here of Sn minus 1. Right? So we define, and this was our goal, it was to iteratively define these functions fn minus 1, and so all the way down to 0. Here we'll have the next function will be fn minus 1 of x. It will simply be 1 over 1 plus r p tilde fn x u plus 1 minus p tilde fn x d. That's our next function. So we have seen this a few times. I just want to make sure we're all good on this. Are the questions on this slide here? Should we try to do it just one more time? So this took us from n to n minus 1. So at a generic point, say that I'm out here in my tree, I'm sitting here with fn, and now I want to go to fn minus 1 of x. How do I get fn minus 1 from fn? Well, I'll do, so at a generic time point, what we need to do is perform the same calculation, but now here having fn of Sn, and then you condition on a previous time point. And you want to write this here as a function of Sn minus 1. Your job is to find Fn minus 1. But you can see what it's going to be. We'll go through the same sort of calculations. We'll replace here Sn by Sn minus 1 times the nth coin flip. Use the independence lemma, and we'll get the function that we're looking for. We'll get the function Fn minus 1 of x. What you need to do is to take 1 over 1 plus r p tilde Fn xu plus 1 minus p tilde Fn xd. And of course, the goal is to go all the way back to f0. Okay, so now what we have is, given all these functions, so given these functions, f0 of x, f1 of x, all the way up to fn minus 1 of x, we can create the initial wealth, we can create the initial stock holdings, the stock holdings at time 1, all the way up to time n minus 1. And how should we do that? So we have the functions now. We just want to do, we want to use these functions to create the initial wealth that is needed to replicate, and what is the strategy, the investment strategy in the stock. Any guesses on what x0 should be? How should we get x0?
S0?
Yeah. And now what about, so that's going to give us the first one. So what about, we also need the stock holdings, delta 0, delta 1, all the way up to the end. And how do we get that? Well, another thing we did last time was, this is also from last time. That we had the self-financing wealth dynamics. The self-financing wealth dynamics, we said that the change in your wealth is given by R times xn minus 1, and then there was plus delta n minus 1 times Sn minus 1 plus R times Sn minus 1. We had that one last time. It took a few pages to calculate, so I'm not going to do it again. So what is it we want? We want we want the replicating property. We want the replicating property that says that xn, just as we had here, this is how we start out. So we want xn to be equal to fn of Sn. Okay, so now what we use is this property here. This is the same as saying what? So here, write this with red, right? This quantity here, this is xn minus 1. So I can move this xn minus 1 to the other side. I'll get 1 plus r. Right? So I'll get 1 plus r xn minus 1, and then the other term. Like I want this to be fn of Sn. But if I'm sitting at time n minus 1 and I want this thing here to be true, the random components, they are inside Sn here. So what I have here, this is really the same thing as two equations. I'll have that this is the same thing as 1 plus r xn minus 1 plus delta n minus 1, and then instead of s, I'll get Sn minus 1 times u minus 1 plus r times Sn minus 1. This is the same thing as fn Sn minus 1 u. This was in the upstate. We also have a downstate, so that's my second equation. So instead of u here, I'll put in a d. This is a minus. This is fn Sn minus 1t. So what I have here is these two equations in either whole. And my unknowns are xn minus 1 and delta n minus 1. We have two equations and two unknowns. We'll go ahead and try to solve them. So we solve for xn minus 1 and delta n minus 1. Let's see if I can do that. So I'm solving for this variable and that variable. I can see I have the same thing here. Okay, so what will I do? I will take, I'll move this to the other side. I'll have fn Sn minus 1 times u minus, and then this part here, this will be delta n minus 1. There's a common factor, Sn minus 1 can go outside. I'll have u minus 1 plus r. And this is going to be equal to, and then I'll get the same term from down here. This will be fn Sn minus 1d minus this term here, minus delta n minus 1 Sn minus 1 d minus 1 plus r. And I solve, so now this is one equation and one unknown. I'll solve for delta n minus 1. I'll solve for delta n minus 1. Maybe we should do it in 2 steps so I don't mess up. I will move this to the other side. So I have fn Sn minus 1u minus fn Sn minus 1d. That was these two. Equals, and I'll move this guy to the other side, delta n minus 1, Sn minus 1. And so that will be the same term. So I have here u minus d. So I can solve for delta n minus 1. This is equal to fn Sn minus 1u minus fn Sn minus 1d divided by u minus d. Just solving one equation and one unknown, I get this. That will give me the the position, but of course I also need the other equation. I need my xn minus 1. So I can get that one from, say, the top equation. I get that one from the top equation. So I'll have 1 plus r xn minus 1. And then here I'll have, I'm missing a term, right? I should have, there should be an Sn minus 1 should be down here too. So if I take this expression here, put it into my top equation, that should give me a way to determine xn minus 1. And let me try to do it. So I have the first term plus n is n minus 1u minus n is n minus 1d divided by Sn minus 1 u minus d times Sn minus 1 u minus 1 plus r. This should be Fn is n minus 1 u. So it's a little bit of a mess, but it's not that bad. We see some of the terms cancel out. There's this common factor there and this common factor there cancels out. Yeah, Patel, this is correct. I was missing this term here. Thank you. So we have a formula now for xn minus 1, and let me try to write it out. So xn minus 1 has a form. It is 1 over r, 1 over 1 plus r. And then a mess. I'll have fn Sn minus 1 u, and then all this stuff has to go over there. Minus fn Sn minus 1 u minus fn Sn minus 1 d divided by u minus d. And now we can see we have common terms. There's a common term here. So we will have that this is 1 over 1 plus r times, and then what we have 1 minus we're missing a term now again. I'm too sloppy here. We're missing a term. So we had this one minus that one, and then there's this term here has to be in there. This is times u minus 1 plus r. This term here had to go down here too. So we have the first one. That was this one. We have this term. That was that term with a minus sign. Now combine. We have here u minus 1 plus r divided by u minus d. This is being multiplied onto fn Sn minus 1u. And then we have the other term. This is the one with the d. It'll be minus, this is a plus. This will be u minus 1 plus r divided by u minus d, fn Sn minus 1 d. Is this stuff looking familiar? I know this was a long, messy calculation, but what do we have here? And what do we have here? What is u minus 1 plus r divided by u minus d?
P risk neutral.
And what is the one we have over here?
P risk neutral.
That's right. Ah, so what does that look like? It looks an awfully lot like what we had here, right? This is 1 over r, 1 over 1 plus r, 1 over 1 plus r, p tilde, fn applied to, well, Sn times u, and over here it's 1 minus p tilde, fn, Sn minus 1 times d. Right? So this here is exactly fn minus 1 applied to Sn minus 1. So there we go, we have it now. We know like this equation here holds true. This equation here holds true if you define delta according to this formula, and if you define the previous wealth according to this formula. What we did, because this is how we started the game, we indeed started out by saying that the wealth at time 0 satisfied this formula. So then you'll get the next property, the one at time n, provided that you define your wealth at, provided that you define your stock holdings at time n minus 1 according to this formula. So this is how you create the replicating portfolio. You start out, this is your initial wealth, and then you iteratively construct these stock holdings using this formula here. And that's how we do it. And then when you get up to the end, you'll get up at time capital N, you'll have X capital N is equal to F capital N of S capital N. And that's the replicating property that you're looking for. So I wanted to show an example for where we have done examples where we've been through this both with a there was a square root we had at some point. We've had a put and a call with numbers. I wanted to do an example that's in our textbook. I try to complicate this a little bit so we move beyond what we've just seen in the last lectures. So I want to move on a little bit further. So this year is what's called Markov process, and this what we're doing is really example 256. So we're saying that not only we're going to have a more general derivatives. Like so before and after. Before we would have Fn of the stock, right? This was the payoff. So more general, in this particular example, we're looking at Fn. It can depend upon the stock, and then it can depend on this Mn. Right, and this Mn, this is a new thing. Mn, this is defined to be the maximum of the stock price. time in. So now this is more general than what we had before, and our job is to compute. We still have to find these functions. We're still going to be looking for. We still hunt f0 of x, f1 of x, but now x should be more general. X here should not just be a function of the stock. It should also be m. So let me write this up. f0 of x and m, f1 of x and m, out to fn minus 1 of x and m. We still hunt these such that what? Such that the conditional expectation of fn applied to the stock at time n and to the maximum at time n given fn minus 1, that this exactly becomes fn minus 1 and then the stock at that previous time and the maximum at that previous time. So the difference is that instead of just having a payoff that depends upon the stock, we're now having a payoff that also depends on the maximum. So is this relevant in the finance world? Well, if you think about, so what kind of options could involve, what kinds of derivatives could involve max or min? Well, the main example of these things is what's called barrier options. Right, the stock has to cross. The stock has to cross, so that's either go above or below some threshold to pay out. So barrier options. So you have if it's a one barrier, you start the stock price, say down here. There's a barrier, and the stock price just moves it around without crossing the barrier. It just expires worthless. If at some point it crosses the barrier, it turns into a put, it turns into a call, something like that. Knock in, knock out. So if it crosses the barrier and then it can continue, then it becomes either a put or a call. These are called barrier options, and these are examples of options that depend upon, say, a max and a min of the running stock price. Right, so for it to cross the barrier, that means that the maximum at some point has to have gone above the barrier. So this is not some academic, it's also academically interesting, but it's also something that people care about. Barrier options, yeah, derivatives that people care about outside the academic world. And so in order to understand them, we need to look at more general derivatives, not just functions written on the stock, but functions that are written on the stock and the maximum. So how would we compute this conditional expectation? Right, so now this is more complicated because there are two things to keep track of. There's both the stock and the maximum. So this is more complicated. So let me try to see if we can calculate. This this conditional expectation. Questions before I launch into another long calculation. We're trying to mimic what we just did before. just in the case where this the derivative pays off depending on what the maximum is, as well as what the current stock price is. So can we calculate the involved conditional expectation? Now we can try it out, see what we get. So we need to understand, so as before, what we want to do is we want to insert what the definitions are. So what's the definition of Sn? Well, that's the one from the binomial model. We're going to write Sn, this is equal to the previous one times the coin flip. Right, and we're going to use then that this thing, this one here, this is going to be independent of Fn minus 1. And we're going to use that this thing here, this is Fn minus 1 measurable. Right, these are the two properties that we've been using over and over, but now we also have this M. We also have this Mn. So we need a decomposition of the same sort as what we had here. Right, so this is equal to the maximum. This is equal to the maximum of Sk from k running between 0, 1, all the way up to n. So we need a decomposition that's similar to the one up here. And so what could we use? Well, it's always about going like one step back. So I want to write this here in terms of, well, the previous one. So how do I express Mn in terms of the previous one? Well, I need to do something to it. These two are not the same. I need to correct this thing here somehow. And so how should I correct it? How should I correct the term here to get a valid equality? Well, what's the difference between Mn and Mn minus 1? Yeah, so it's something with S. So when is Mn the same as Mn minus 1? Well, that depends on what the stock price was at time n. So if I put in here, if I write this here as a max of Mn minus 1 and Sn, then this should work, because to get the maximum at time n, I look at the maximum up to and including n minus 1 and then the current value. And that's going to give me the current running max. And so now I have it, because this here is the maximum between Mn minus 1, Sn, I use the formula we just had. This is Sn minus 1 and then my psi. Right, so as before, this thing here, this is Fn minus 1 measurable. So is this one. And this one, this is independent of Fn minus 1. And that's what I need to use the independence lemma, and then I'll carry on, compute the conditional expectation. So by the independence lemma, we have, I'm holding the conditional expectation of Fn Sn Mn given Fn minus 1. I'll write out what it is by inserting the two expressions for S and M. I'll get that this is E tilde, get that this is E tilde of Fn. Instead of S, I'll have Sn minus 1 by psi. Instead of Mn, I'll have a max of Mn Sn minus 1 by psi. Conditional Fn. I'm running out of paper here, but so what I did was I replaced what Sn was and what Mn was, and I get this mess on the right hand side. Now I invoke the independence lemma. So the independence lemma, this part here, is going to come in this equality. You take out, you replace everything that is, this is Fn minus 1, anything that is measurable with respect to Fn minus 1, and then you take the average over the rest. The only thing that is not measurable, this is my size, psi n, this is independent, so I take an average. So I'll get here that this is P tilde, this here is P tilde times Fn of Sn minus 1. Instead of psi, I'll put in my u. I'll have a max Mn Sn minus 1. And then instead of my psi, I'll have a u. That was the first term, plus. And then I also need to take into account that xi could be d. So I'll get 1 minus P tilde. Fn Sn minus 1 d max Mn minus 1 Sn minus 1 and then a d. This allows me to finally find this this previous function Fn minus 1. I need a discount factor, it should be 1 plus r here. I'll take the conditional expectation divided by 1 plus r, and this will give me the wealth at the earlier time. So I'll get, so Fn minus 1 of xm, this is going to be 1 over 1 plus r, and then we replace Sn minus 1 with an x. And the max, replace Mn minus 1 with a dummy m. So x times u plus 1 over 1 plus r times 1 minus P tilde Fn xd max m xd. So that's the previous one. So given a function, given a payoff function now of 2 variables, so the stock and the running max, you're given a function here that depends upon both of them, and then you iterate backwards. Backwards, and you're going to get this string of functions, and then you go all the way back to time 0, get f of 0, x comma m, and that's going to be your initial well. Then you move forward, creating these deltas as we did before, and then you'll move forward. You have to adjust this formula here to take into account that these functions fn are no longer just functions of the stock, but you also need m in there. There's some things to note here, and that is what happens in an example where the payoff only depends on the max. So a special case. Could be Fn only depends on Mn. Right. So an example could be you're going to get $1. You're going to get $1 if the max is bigger than, I don't know, 10. This here is your function. This is your Fn of m. Right, so it pays out $1 if the maximum of the stock price over the period has gotten above 10. If it has not gotten above 10, it would not pay out anything. So if you look at this case, then do we really need Fn of x and m, or is Fn just of m sufficient? Right, so here we will have the payoff would be Fn of Mn, right? There's no stock appearing directly in the payoff function, it's just a running max. So then you could wonder, when you go backward iteratively, would you really need to keep track of also the stock as well as the running max? Or is it sufficient just to keep track of the running max? And the answer is, so this here is, in technical terms, we are asking if this running max of the stock price is a Markov process. Well, let's just try to work it out. The way to get started on stuff like this is to just start out with the end and see what happens when you compute the conditional expectation at time n-1. Right, so we need to compute the conditional expectation of Fn, and then we'll plug in Mn here, given Fn minus 1. The question is this a function? Is this a function of, is this a function just of Mn minus 1? We know that if I include also Sn minus 1, we're okay, but can I express the left-hand side just as a function of the running max? So we know that we can write this here as a function of Mn minus 1 and then Sn minus 1. But is it sufficient just to have M here? In other words, is M by itself what's called a Markov process? And the answer is no. This is not true. This is not possible. This is not possible. And to see that, we compute once again the conditional expectation. We compute once again the conditional expectation, and the way we do it is use that formula. We'll once again compute the conditional expectation using this formula we have here. This here is Fn, and then instead of Mn, we will put in the maximum of Mn minus 1, and then the stock Sn. Given Fn minus 1. And so you use the independence lemma. We use the independence lemma, we take out what's known. We take out what's known and take the average of the rest. So this Sn here, we have seen him a number of times. This is Sn minus 1 and then my psi n. So what I'm left with is Fn times p tilde applied to this max, Mn minus 1, Sn minus 1, and then times u plus 1 minus p tilde Fn max Mn minus 1 Sn minus 1 times d. And so the question is this equal to a function of Mn minus 1? And as you can see, this is not true because there's both Mn minus 1 in here, but there's also Sn minus 1 in here. So it's not sufficient just to know what the max is at time n minus 1. We also need to know what the stock price is at time n minus 1. This here is not a function of Mn minus 1. Could we follow this last bit here? So what we started out with was we had a desire to generalize. If we wanted to price barrier options, we cannot express the payoff of a barrier option just in terms of the current stock price. We also need to keep track of the running max or the running min if you want to price barriers. So we move away from having payoffs that just depend upon the stock to having payoffs that depend about both on the stock as well as on the running max or running min. And so we go through the motion and we get these functions that depends upon both the stock and the running max to get the conditional expectation. So now we're asking, what about in this special case? In this special case where the payoff only depends upon the running max. So there's no stock appearing in the payoff at the end. Is it sufficient? Is it sufficient then just to keep track of the running max in these functions, or do we really need to include the stock as well? It's easier to keep track of just one process inside here than it is to keep track of two. And the answer is, unfortunately, that you have to keep track of both, because if I just go back one period, even though my terminal payoff only depends upon the running max, as soon as I perform the conditional expectation, I'm going to get something that depends both on the running max as well as the stock. Right? I can't write this here as a function of Mn minus 1. I'm missing this. Are there questions on the Markov? So now next I'll define specifically what a Markov process is, but what about the reasoning here on the piece of paper? Can we follow the calculations? Can we follow the calculations? Okay, so let me bring up the homework. We'll bring up the homework. So this here is the homework 6. So you can see again there is a maximum, and the question is do you have these Markov process properties? We're going to define that soon. So that first question here in the homework that's due is what we have just done. Then there is there are optional problems over here in the end, and here there are there's more practice on like what does it take if you don't have the property that we had before. Like, so if we just focused on M by itself was not Markov, so you would have to include more processes in order to make sure that when you do this conditional expectation calculation, you would get you'll be able to express the resulting random variable as a function of these however many processes. And this is what this optional problem 1 here is about. So I put up how many are there? 6. And so if you find what we just did a bit challenging, this optional problem 1 here, as well as the first homework problem, this is really what this is trying to help with. So what I'm going to do now is I'm going to write down the formal definition of what it means to be a Markov process. So what's the definition? So a process so say a process X is a Markov process. So X here could be Xn, could be a vector, like what we just had. So I shouldn't call him X, maybe I should call him Y. I'll call him Y instead. Could be a vector like Yn would be Sn and then this Mn. So take a stochastic process. This is called a Markov process, or it's called the textbook like to call it a state process. A state process and a Markov process. These two expressions, they mean the same in quantum finance. If, so here comes the condition, if for any function that goes, if for any function we'll have that the conditional expectation of f applied to yn. If for any f I can find a g such that the conditional expectation at time n-1 can be written as that function applied to the state at this earlier time. So going back to the example, so going back, to the example, we could start out by saying yn is just s. Is it true that when I compute the conditional expectation of f of yn given fn minus 1, is this really just a function? So give me any function, can I find another one such that this is true? Is it really true that I can write this here just as a function of Sn minus 1? Is this here equal to g of yn minus 1? You guys are very quiet today. If I look at the stock price, is the stock price a Markov process? Is it true that I can find a function such that the conditional expectation of the stock at a later point is just equal to that function applied to the current stock price? We can put it here on the tilde, we can put it on. So here I did it on the P. Is that true? Yeah, and how would you do it, José? How would we do this? So the answer here is yes. I like it. And how would we do it? Well, we start working on the left-hand side. When we follow the usual procedure, we write this as an expectation, f, and then we'll plug in Sn. So this will be Sn minus 1, the psi, given Fn minus 1. And then how would we work from here? Well, we use the independence lemma. We'll use the independence lemma, and we'll write this here as, if I am on the P, this will be a P. And then it'll be f of Sn minus 1 u plus 1 minus P times f of Sn minus 1 d. So my function g of a, this is p f au plus 1 minus p f a d. So then we go back to saying what happens if my y is two-dimensional. If my y is two-dimensional, I will have Sn and then this Mn here. Can I write a conditional expectation of f of yn given fn minus 1? Can I write this as a function just of y at that earlier time? Is that true? Can I do that? How would we attack it? We would try to do the same thing as before. We would write this as an expectation. If now y is two-dimensional, so we start out with Sn. This will be Sn minus 1 times psi. And then we have the maximum. So this will be the maximum of Mn minus 1 and then Sn. So here we have Sn minus 1 psi. So we use the independence lemma one more time. I'm still calculating on the P. So I'll get here, this will be P, F, will be Sn minus 1 times U, comma, max. And then it'll be M n minus 1, Sn minus 1, U, plus 1 minus P, F Sn minus 1, D, max, Mn minus 1, Sn minus 1, and then a D. Is this here a function of Yn minus 1? Well, what is Yn minus 1? This quantity here. This is my Sn minus 1, my Mn minus 1. And so you look at what's on what you found. This is a function of Sn minus 1, and it's a function of Mn minus 1. So yeah. The answer is yes. And then the last one we discussed was, what about, so we're at 9, this is page 10. Page 10, page 11. What about if I take Yn just to be the max? So this here is the max. The maximum of the stock price along a given path. Would that work? So pick a function, plug the max into it, compute the conditional expectation. Is that going to be a function just of the value that the max has at the time of a condition? Well, how would we do it? We would, for example, we would try to work out what the left-hand side is by inserting what y is in terms of previous values. So we work out what the left-hand side is. This is f. And then what's the max at time n? This is going to be the max at time n minus 1, and then the current value. So the current value was Sn. So that's this Sn minus 1 times psi, condition on n minus 1. Does this look like a function of Yn minus 1? Well, we have to calculate what we have here. We again use the independence lemma. This is P, if I'm computing on the measure P, of f of max of Yn minus 1 is n minus 1, and then you have a u here, plus P, 1 minus P, f of max Yn minus 1 is n minus 1 times d. Now, is this a function? This here should be m. My y, this should be m here. This should be m here. Is this here a function of f of what is yn? This is m n minus 1 is n minus 1. So Jose is right. The answer is no. This is not true, because we also need this thing. Also S is needed. So state processes and Markov processes, they're quite important. They are, whenever you want to price a derivative, the first thing to do is to figure out what is the payoff. And that's the starting point for pricing derivatives. You're not going to get anywhere without knowing what the function is. Okay, so the function is given to you in the problem. That's how it is. You look at all the exam problems and all the TA sets that we talked about. The function is given. And okay, so it's given as a function of something quite often it's a stock, but not always. If you're looking at barriers, you'll also have something with a max or a min in there. So then the next thing you need to figure out is, okay, so what is the system of processes that I need to keep track of? And the way to get started on that is to calculate like one step back. So you go from Fn to Fn minus one. So you calculate one step back, which is what we've been trying to do here. Because go back one step and see how much do you need to keep track of. Is it okay just to keep track of one component, or do I need both of them? And the mathematical expression for that is you need to figure out what the underlying macro process is. And as I said before, math finance folks, so math finance folks, I call these state processes. And then this is including our textbook. So you need to figure out what the states are, and the state processes. Those are the ones you have to keep track of when you perform this conditional expectation calculation. And so when you figure this out, you form all these functions Fn as we did before. Given that you have all your f's, well, then you can create your x0 and you can create all these deltas using the formulas that are on this sheet. And then you price the option, right? You found the replicating portfolio and you found the initial wealth that is needed to set up this replicating portfolio. Therefore, the replicating, the arbitrage-free price of this derivative is just going to be given as this f0 applied to s0, and potentially more variables you'll need in here. If your terminal payoff depends upon the max, then you also have to have the maximum in here times 0. Other questions on this, or is it time to take a little short break? So as usual, we need to switch to a different Zoom ID. There was one student who said that I messed up the scheduling of that student's exam. Can that student please identify him or herself, and or either send me an email so I can get this fixed. Try to get it fixed here in the break. Otherwise, I'll see you in about 10 minutes at a different Skype login, a different student login.
Hi, Professor Larson.
Yes.
This is Kashif. I earlier mentioned that I've given my preference for the test.
Okay, and what's your last name again?
Anwar.
And I messed up, huh? Anwar Afif?
Yes.
Were you in a different class of mine at some point?
No, this is the one where I am.
So I am not seeing this email. Did I get you? You're saying you did not appear on the...
So, I mean, it comes differently on Zoom. It comes as Everest there.
Okay, let me just find the people.
Should I give my like login ID, like net ID?
I should be able to find your email. ANVER.
ANWER.
Oh boy, you didn't write the class on this. It was on October 23rd, 9 to 10. Let me just see. Did I get you put into the wrong? hang on. Yeah, you got schedule on the wrong one. Oh gosh. And now,
Because I've planned my stuffs accordingly, Professor. So
I
I'm
understand.
taking like Thursday leave at my work.
Uh, so I'll have to put you in. Would 12 o'clock work?
Which one?
Would 12 o'clock work?
Yeah. Any time on Friday would work for me.
Yeah, I get it. So I'll have to put you in at 12. This is my bad. Okay, so let me just make sure. 12 o'clock. Right. Sorry about that.
No problem, Professor.
Okay. I'll talk to you later.
Sure.